These are notes for AP Calculus on the topic of Taylor series. So we've looked at Maclaurin series, and Taylor series are very, very similar. Maclaurin series is a specific type of Taylor series, and the most common kind, where it has derivatives of all orders at x equals 0. Well, Taylor series are more general because they don't have to be at x equals 0. They could be at x equals a, where a is just some constant. So when that's the case, notice there's a couple things different about the formula when it's about x equals a as opposed to when it's about x equals 0. Well, if x equals 0, you just have x to the n on the Maclaurin series. Notice here when it's x equals a, we have x minus a to the n. That's one of the differences, whatever that constant happens to be. So if a was 1, it'd be x minus 1. If a was negative 1, it'd be x plus 1, and so on. And then notice the a value also appears here, the nth derivative at a. Before, this was always 0 because Maclaurin series, it was always about x equals 0. Otherwise, they follow the same pattern as a Taylor series. So notice when we write it out here, the first term is the 0th derivative of the original function at a. Now it really has x minus a to the 0, but that doesn't show up because the 0 power, that's just 1, and it also is divided by 0 factorial, but that doesn't show up because that's 1 as well. The next one has the first derivative, x minus a to the first, over 1 factorial, which you don't need because that's just equal to 1. And then the same pattern. It's the second derivative at a, ax minus a squared over 2 factorial, so all the same. Then the third derivative at a, x minus a cubed over 3 factorial, and so on. So otherwise, the pattern is just like the Maclaurin series. All right, so let's see if we can write the first 3 non-zero terms and the general term of the Taylor series for 1 over x plus 2 squared about x equals negative 1. So that's our a value. So notice this one is not a Maclaurin series. It's not about x equals 0 like we've been focusing on up until this point. So let's write down the pattern so we can see a little easier. Again, I'm going to start with 0 so you can see the pattern a little better. So this is going to be the 0th derivative, in other words, the original function. F of not 0, though, a value is negative 1, so f of negative 1, the 0th derivative. And then it's x minus a, but minus negative 1 makes it plus 1 to the 0th power over 0 factorial. That would be our first term in the Taylor series. You can see a lot of things are going to simplify there. Plus, the next one would now have the first derivative, so f prime of negative 1, right value. They'd have x plus 1, this is the first derivative, to the first power over 1 factorial. And then plus f double prime of negative 1, x plus 1 squared over 2 factorial. And then let's wait on the general term until we can see the pattern a little more easily. All right, so this is our original function. This is f of x. So if we rewrite this, it might be a little easier. Because if you leave it like this, you could use the quotient rule, but since it's just a constant on the numerator, if we move this up to the numerator, that's the same as x plus 2 to the negative 2, and that makes it a little easier to find our derivative. So then the first derivative, f prime of x, using the power on chain rule, bring down the negative 2 exponent, and then it'd be x plus 2, you'd reduce the exponent by 1, so negative 3. And then using the chain rule, the derivative of the inside, you'd multiply by it, but in this case it's pretty simple because the derivative inside is just 1. So just times 1, that doesn't change anything. And then our second derivative, notice since we need the first 3 non-zero terms, we'll need up to the second derivative at least. So f double prime of x would be negative 3 times negative 2 is positive 6, x plus 2 to the negative 4. So let's see if we can find f of negative 1, f prime of negative 1, and f double prime of negative 1 now using these 3. So let me simplify each of these now. This one's going to go back to this one. It'll be easier to substitute in. 1 over x plus 2 squared. The first derivative, f prime of x, would simplify to be now 2 over x plus 2 cubed. And the second derivative would simplify to be 6 divided by x plus 2 to the 4th. And if we substitute in negative 1 into each of those, well, let's try f of negative 1. Well, that's negative 1 plus 2 is 1, squared is 1, so 1 divided by 1 just gives you 1. Then f prime of negative 1. Again, negative 1 plus 2, that's 1 cubed is 1. 2 divided by 1 is 2. And f double prime of negative 1. That being negative 1 plus 2 is 1 to the 4th is 1. 6 divided by 1, 6. So, if we substitute those in, let's see what we get. All right. Well, this is going to be 1, right? This is to the 0 power, that's 1. 0 factorial is 1, so everything, 1 times 1 divided by 1, that's just 1. Is our first non-zero term. Notice they're only going to be 0 if this derivative or the original function we plug in negative 1 is 0 for any of these. In this case, we didn't get 0 for any of those, so we're fine. F prime of negative 1, that was 2. Divided by 1 factorial is just 1, so that's just 2, so plus 2. And then, sorry, it wasn't positive 2. Made a mistake here. This was a negative 2 here. Sorry about that. So that makes this negative 2, so it'd be negative 2. And then x plus 1 to the first is just x plus 1. And then f double prime of negative 1 we got was 6. So that's 6 divided by 2 factorial is 2 times 1. 6 divided by 2 is 3. So plus 3 x plus 1 squared. Now, depending on the problem, sometimes it's easier to write the general term using the unsimplified form. Sometimes it's easier to use it. In this case, it'll be easier to see the pattern with the simplified form. So our general term here, go plus, dot, 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 to show all the terms in between. Notice we've got x plus 1. Well, first, notice it's an alternating pattern. So we need negative 1, and the first term is positive, so to the end, that way when you plug in 0, you get a positive term. Then notice the number out in front is 1 larger than the exponent. So right here, we'd have x plus 1 to the n, right? When 0, you don't see it. 1, you have 1. 2, you have 2. But since this number is 1 larger than that exponent, you could write n plus 1. And then plus, sorry, whenever, and then dot, dot, dot. So there would be our first 3 non-zero terms and the general term for that Taylor series. Okay, let's take a look at one a little bit different now. This next one, we're given the formula here. It says f has derivatives of all orders between when x is between negative 1 and 5. And notice we're asked about at x equals 2, which is in that interval, so the derivatives all exist at 2. And the derivatives satisfy the conditions below. This time we're given f of 2 is 1, and then we're given a formula to generate the nth derivative at 2. And that formula is n plus 1, whatever derivative is, plus 1 factorial divided by 3 to the n, for all n greater than or equal to 1. So starting with the first derivative. All right. So this one, though, says write the first 4 non-zero terms and the general term of the Taylor series about x equals 2. So there's our a value 2. So let's write out the pattern first for the Taylor series. So it's going to start with the 0th derivative at 2. So the first term will be f of 2, and then x minus a, which is 2, to the 0th power over 0 factorial. Again, I like to write it, even though we know this is going to simplify, just to get the pattern started. It's kind of easier to follow through, I think. If you can do it without it, that's fine too. Plus, now we'd have the first derivative at 2, x minus 2 to the first over 1 factorial, 1, 1, and 1. And then plus, then you'd have the second derivative at 2, x minus 2 squared over 2 factorial. And then plus the third derivative at 2, x minus 2 cubed over 3 factorial. And as long as none of these are equal to 0, that will give us our first 4 non-zero terms. Again, let's try to write the general term at the end to see what the pattern is. All right, so let's go ahead and find, well, we already know f of 2, So we need the f prime of 2, f double prime of 2, and f triple prime of 2. Let's find each of those. So here's our formula here. We're just going to use that to find f prime of 2. Well, if n is 2, n is in this case 1, right? It's the first derivative. That would be 1 plus 1, so that would be 2 factorial divided by 3 to the n is 1 to the first, so that's 2 factorial is just 2 times 1 is 2, divided by 3 to the first is 3, so that gives you 2/3. So f prime of 2, which will go right here, is 2/3. Then f double prime of 2 would be, if n is 2, that would be 2 plus 1, that would be 3 factorial over 3 squared. Well, 3 factorial is 3 times 2 over 3 squared is 9. Gives you 6 over 9, which just happens to reduce to 2/3. So does that mean they're all going to be 2/3? Well, let's find out. F triple prime of 2, following that same pattern there. This time n is 3, so it would be 3 plus 1, which is 4 factorial, divided by 3 to the n is 3, so 3 to the third. So 4 factorial, 4 times 3 times 2 times 1. You could write it as 27, or another way of thinking about it is just 3 times 3 times 3 is 3 to the third. And notice what reduces here. One of those 3's reduce that. It'll just be 1, and that's it. So we're left with 4 times 2 times 1 is 8, over 3 times 3, 9. So they aren't all 2/3. Those two just happen to be the same. So if we substitute those in, f of 2 we're given as 1 right here. So that we can put in right here. That's 1. X minus 2 to the 0 is 1. 0 factorial is 1, so the first term is just 1. Plus f prime of 2 was 2/3. Divided by 1 factorial, that's like divided by 1, so that's just 2/3. So it's going to be 2/3 x minus 2 for the first, so it's just x minus 2. F double prime of 2 was also 2/3. But this time it's divided by 2 factorial. So if we have 2/3 divided by 2 factorial, that's 2. It's the same as multiplying by the reciprocal 1 over 2. The 2's reduce out, gives you 1/3. So it would be plus 1/3 x minus 2 squared. And f triple prime of 2 was 8/9 divided by 3 factorial, which is 3 times 2, which gives you 6. So 8/9 divided by 6 is the same as multiplying by the reciprocal of 6, 1/6. And you can see you can reduce that a little bit. You can divide that by 2 gives you 3, divided that by 2 gives you 4. So you get 4 times 1, 4, over 9 times 3, 27. So we get plus 4 over 27, x minus 2 cubed. So there's our first 4 non-zero terms. Plus, let's see if we can write the general term. Now in the previous problem, the general term, we could tell the pattern pretty easily from here. It was 1, 2, 3, and then the next term would have been 4. You can see it was just one more than the exponent. Sometimes that's easier to tell. On this one, however, 1, 2/3, 1/3, 4 over 27, it's a little harder to tell the pattern, isn't it? However, remember, we don't need to tell the pattern because in a sense we were already given the pattern right here. This was our formula for the nth derivative, right? That's how it's generated. The only thing we can't forget is it's also divided by this n factorial. So to get the nth term, notice this one is not alternating. We don't need that -1. So where these numbers are coming from is this formula we used right here, right, to calculate the nth derivative at 2. So they're giving it to us right here. So the n plus 1 factorial, and then divided by 3 to the n. But then don't forget, we still have this x minus 2 is part of our formula for the answer, to the n power, right? That's 0, then 1, 2, 3. And then don't forget, it's also got this n factorial there. So divided by n factorial. So we just have to put it together, the rest of it, plus dot, dot, dot. So there's our first 4 non-zero terms and the general term. And again, if you're not sure if this works, you can always test it. You plug in 0, that's 1 factorial, that's to the 0, that's 3 to the 0 is 1, 0 factorial is 0, 1, so they're all 1, so you get 1. If you substitute in 1, you get 2 factorial, x minus 2 to the first, over 1 factorial is 1, 3 to the first is 1, so 2 factorial is 2, divided by 3 to the first is 1, gives you 3, and so on. And it should work as long as we calculate these correctly, because we did use that exact same formula to find the nth derivative for each term in our Taylor series. All right, let's take a look at the next one. On the next couple, we're just looking at one specific term. Notice it asks for the coefficient, remember that's the constant out in front, of x minus 4 cubed in the Taylor series about x equals 4. So there's our a value for this function right here. Okay. So for x minus 4 cubed, now we're just focusing, instead of the first 4 terms or first 3 terms, we're focusing on one specific term. So let's follow the pattern for the Taylor series. If it has x minus 4 cubed, right, well, what else would have to be in that term? Well, we would also need this derivative, right? In this case, the third derivative, so it'd be f triple prime of, what's our a value here? It's about x equals 4, so you can see that here as well. So the third derivative, 4. And then divided by that same number, factorial, 3 factorial. So when it says the coefficient, it's really talking about this part, right? That's going to give you the coefficient of x minus 4 cubed. So that's what we have to calculate. 3 factorial we can already calculate, but we don't know the third derivative at 4 yet. So that's the part we have to figure out in order to figure out that coefficient. So this is our original function. So this is f of x. Again, you could use the quotient rule there, but since we need to get to the third derivative, that could take a while if we had to keep using the quotient rule over and over again. It's simpler. Again, we just rewrite this since the 2 is just a constant as 2x minus 3 cubed. Then we can take our first derivative just using the power and chain rule. 3 times 2 is 6. Reduce the exponent by 1. So, oops, sorry. My mistake. I forgot the negative on the exponent. So that should be negative 3. So negative 3 times 2, negative 6. X minus 3, subtract 1 from the exponent to the negative 4th. Use the chain rule, but the derivative inside is just 1, so it doesn't change it. Then the second derivative, negative 4 times negative 6, 24. X minus 3 to the negative 5. But we need the third derivative. So f triple prime of x would be negative 5 times 24. Well, negative 5 times 20 is 100. Negative 5 times 4 is 20, so negative 120. X minus 3 to the negative 6, again, just multiplied by the derivative inside is 1. If we simplify that, that's negative 120 over x minus 3 to the 6. There's our third derivative. And notice we just need to substitute in 4 into that. So f triple prime of 4 would be negative 120 over 4 minus 3 to the 6. But that's just 1 to the 6th power is just 1. So you just end up with negative 120 over 1. So what we have here, to bring this down, we can substitute that right in here, because now we know what f triple prime of 4 equals. So it equals negative 120, this is our coefficient, divided by 3 factorial. But 3 factorial is just 3 times 2. So that's negative 120 divided by 6 is negative 20. So that would go with the x minus 4 cubed term. But we're just asked for the coefficient. If we're asked for the whole term, that would be it. But since we're just asked for the coefficient would be negative 20. All right, let's take a look at another one where we're focusing on one term here. It says we've got, this case though, they make it a little easier because they already give us the fourth derivative right here. This is the square root of 1 minus 4x. And again, we're just looking for the coefficient, this time of x plus 2 to the 5th in the Taylor series about x equals negative 2. So let's look at that specific term. If it has x plus 2 to the 5th, well, what else would it be in it following that Taylor series pattern? Well, it would have to be the 5th derivative, right? Since it's to the 5th power. And what would you substitute in? Well, you can see from here or here, it's a negative 2. X minus negative 2, that's what makes it x plus 2. so the fifth derivative of negative 2, divided by 5 factorial. All right, so the coefficient, again, it's going to refer to this whole thing out in front. That's going to be the coefficient of x plus 2 to the fifth. That's what we're looking for. So notice we need the fifth derivative of negative 2. But unlike the other one where we started with the original function, this one's a little easier because we're already starting with the fourth derivative. So we don't have to take the derivative 5 times, we just have to take the derivative once to get to the fifth derivative. So since our fourth derivative, let's rewrite this here. Make it easier to take the derivative of. We could write it as 1 minus 4x to the 1/2 power. So then when we take the fifth derivative, it's just the derivative of the fourth derivative using the power and chain rule. That would be bringing down to 1/2, 1 minus 4x to the negative 1/2. But using the chain rule, the derivative inside, the derivative of 1 is 0, but the derivative of negative 4x is negative 4. So times negative 4. And then let's simplify this first. So the fifth derivative of a function. Well, negative 4 times 1/2, that's negative 2. And then if we move this to the denominator, because it has a negative exponent, put it in radical form, over the square root of 1 minus 4x. And then what we want is we want the fifth derivative specifically at negative 2, so let's just substitute in negative 2 now. So the fifth derivative at negative 2 would be negative 2 divided by the square root of 1 minus 4 times negative 2. Well, that's negative 2 divided by, well, negative 4 times negative 2 is, remember you got to multiply before subtracting using order of operations. That's positive 8 plus 1 gives you 9, so that's the square root of 9. But the square root of 9 is just 3, so you have negative 2/3. So that's what we can substitute in right here. So our coefficient would just be negative 2/3 divided by 5 factorial. Well, that's the same as negative 2/3 divided by 5 factorial is the same as multiplying by the reciprocal by 1 over 5 factorial. Sometimes you might see it left like this, but oftentimes, especially when things reduce, you'll see it worked out. So let's go ahead and work this out and see what reduces. 5 factorial is 5 times 4 times 3 times 2 times 1. Notice what reduces here. The 2's reduce out. And then what we're left with is negative 1 over, probably the easiest way I think to do this is if you multiply the 5 times 4, that's 20. 3 times 3 is 9. And 9 times 20 is 180. So it'd be negative 1 over 80. Again, this would be the coefficient of x plus 2 to the fifth, but we're only asked for the coefficient, so you don't have to write that part down. It's just the negative 1 over 80.